Hello. Today I'm gonna be teaching you how to use a pseudo-steady state approximation for reactive intermediates. My name is Carter Van. I'm in class Chem MTC and the professor is Jim Smith. Today's date, April 21st, 2021. Now, as for what pseudo and steady approximation for for reactive intermediates. I'm going to be using these three main sources, but in large part going to be using this one because that's where I found the majority of my research and all that from. Now, pseudo-steady approximation for reactive intermediate. What is it? Well, the importance is that it makes the derivation of rate expressions much easier. It applies when an intermediate reacts as it's generated. And the simplest way to show it is when the K2 is greater than the K1. The K2 happens to be, as you can see right here, K2 being the second step in the reaction and K1 being the first step. And there are many equations for this. As you can see from this, the image from WikiWand that I found, it shows how the red is the concentration of the reactants is decreasing, whereas the blue shows the what's called the products is increasing over time. And this image that I found off LibreText shows the steady state zone of it increasing over time, then staying steady. That's pretty much it. Yeah. Now, for how it is derived, I meant. As you can see from here, step 1 and step 2, A makes B, B goes to C. And from this we can derive that A, B, C. And from this we can gather that B is the intermediate because it happens in between A and C. So in essence, the reaction is just A to C. And from that we can derive this equation in which D times the concentration of B over time is equal to 0, which is equal to the K1, A, concentration of A, minus K2, concentration of B. And if we want to get B by itself, we will get this. The concentration of B is equal to K1, concentration of A divided by K2. What K is it's the reaction rate of the expression or the reaction. Yeah, it's the reaction rate, how fast everything happens. And the reason why this equals 0 is because K2 is K1, is greater than K1. And because the intermediate is being consumed faster than it is being produced. And as for the reaction mechanism, we can see that D times the concentration of C divided by dt equals to K2 times the concentration B is equal to K2 times K1 times the concentration of A divided by K2. So in essence, the K2 right here and the K2 right here cancel each other out, just giving us K1 times concentration of A. So as you can see, that means the K reaction of K1 times concentration of A is equal to K2 concentration B. And if we want to get C by itself, we will get this equation, which is shows how the concentration of the product is made. So concentration C is equal to the initial concentration of A times 1 minus E raised to the negative K1 times T, T being time. And now if you want to see an example of this, you can see the starting of it is 2 NO2 gas plus O2 gas makes 2 NO2 also gas. The first elementary step of this is NO plus NO makes N2O2. And the second elementary step is N2O2 plus O2 makes 2NO2. And if now what we want to do is we want to add these two together so we can get the overall reaction. As you can see, there's N2O2 on both sides, so we can cross those out and they kind of cancel each other out. This leaves us with NO, NO, and O2. And from that, we can gather that there's 2 NO, so there's a 2 here, and an O2. So there's only one. And if we check, that does make sense because everything happens. We don't have to really change anything. There's two NOs, two here, two, two, two. See? And then we get that reaction. We check it if it's balanced, and it looks like it is. And so pretty much the overall reaction is pretty much the same as this, funny enough. As for the reaction mechanism, we can gather that N2O2, being us, the intermediate, is what we want to set it equal to 0. As aforementioned from the previous slide, how it is equal to 0 because the intermediate is being consumed faster than it is being made. So equals 0 equal K1NO minus K2N2O2. And if we want to get N2O2 by itself, we get this equal to K1NO divided by K2. And if we want to get NO2 in there, for the end product, we do this. D times NO2 divided by DT equals to K2 N2O2 equals to K2 K1 times the concentration of NO divided by K2 equals K1 times the concentration of NO. And that gives us the final what's called concentration of NO2 equals to the initial concentration of NO times 1 minus E raised to the negative K1 T. And that's pretty much an example of how you do the steady state approximations. But otherwise, usually it wouldn't be like this because you would have numbers like concentration of like 5 moles of N2O2 or something like that. And using all this, you would get a number for the actual concentration of whatever you want. Or if you're looking for K, you would find the concentrations of all these, and you would find the actual reaction rate of all this. Now, in conclusion, this is supposed to be helpful in helping you find multi-step equations like this, where you can use like the elementary steps and pretty much just cross out all what's needed and get what the overall reaction is left, and then plug it into the equations, derives the overall rate expression, and it pretty much applies as soon as an intermediate reacts as quickly as it is generated, if not consumed faster. And as you can see, this top one helps you find the concentration of the what's called the end product, and this is pretty much helps you find the concentration of the intermediate because it equals 0 because the intermediate is consumed faster than it is being generated. Yeah, that's about it.